Okay, see Lindelof videos, calculos, proof that ddx of sine of x is equal to cosine x, and your professor is going to want to see this through the limit process, so I'm just going to establish the limit process, which is right here. Remember, as you pursue the limit process, after you write f prime at x the first time, you don't have to continue to write that, but you do have to continue to write limit as change in x approaches 0. So I'm just going to write limit as the change in x approaches 0 of, and I'm going to fill in the blanks here, and my first function was sine of x plus change in x minus sine x, right? Just following the example here, all over change in x. Here's where I think, sorry, I'm just going to say it, I think this is where professors kind of blow it, because they put something in here, they make this assumption here, and they assume that we remember this sum and difference rule. In trig, there is the sum and difference rule, sum and difference rules, and we're going to use the sum rule, which says this, that if we have sine of alpha plus beta is actually how it's usually written, that can be rewritten as sine alpha cosine beta plus sine beta, I should have written it the other way, cosine alpha sine beta. And this is that sum and difference rule. So that's all I'm going to do here. I'm going to apply this trigonometric rule to this problem, this calculus problem here. So that's where I'm coming up with this crap here. So I'm going to declare this. I'm going to start with the limit process again. Limit as the change in x goes to 0. Instead of writing this, I'm going to use this sum and difference rule. So that's going to end up being sine x, right? Cosine change in x plus cosine x sine change in x, and then remember we have this minus f of x. Well, my f of x is sine x, so minus sine x all over change in x. It looks like hell, doesn't it? It looks awful, and I apologize, but it's cool. We're going to be fine. What I am going to do is I'm going to move some parts around. I'm just going to move this piece to over here. So I'm just going to rewrite it again, because your professor is going to demand that you continue to use correct convention. So I'm going to take sine x cosine change in x, and I'm just going to move this piece to here, minus sine x plus cosine x sine change in x all over change in x. I'm going to factor from this piece right here, if you don't mind. I'm going to factor from this piece right here. And when I do that, I'm going to get sine, right, I'm going to get sine x times cosine change in x minus 1. Isn't that right? And then while I'm doing it, I'm just going to partition this out a little bit. I'm going to take a double limit, which is fine. You can do limit by parts. It's absolutely fine. No problem at all, because they're going to add up to the same. So right there, isn't it? This plus sign is this one, and now I'm going to have here cosine x over sine change in x. Now what I'm going to do is I know another rule, and the other rule I know is that 1 minus cosine x over x is equal to what? Is equal to 0, isn't it? So it's equal to 0. So check this out for just a second. I'm going to factor out a negative 1. I'm going to rewrite this again. Limit as the change in x goes to 0 of negative sine, you'll see what I'm doing here, see this negative right here, is 1 minus cosine change in x. And if you look carefully, if I multiply this negative times this positive, I'll get this negative 1 here, and if I multiply this negative by this negative here, this will go positive. So all I did was factor that out so I can use this rule, all over change in x, plus cosine x. If you don't mind, I'm just going to let you look at it a little bit weird. Sine change of x over change of x. All I did was just factor this out. It's still there. It's over 1, and if I multiply it, go right back, wouldn't it? Because I know some stuff. I know this rule. I know that 1 minus cosine x over x is equal to 0. So this thing right here now equals 0. So I have the limit as the change in x goes to 0 of negative sine x times 0, because this whole thing goes to 0. This piece right here is 0, plus cosine x times, now I know this rule, and this is the second rule I know, so I'm going to take a look at this. So what's happening here is I'm going through all of these special trig differential derivatives. I know, because my professor enlightened me, that sine of change in x over change of x, sine of x over x is equal to 1. So this takes on a value of 1. So this is 1. So look what happens here. Now I'm done, because I have d dx of sine of x, which is where I started, is equal to cosine x. Pretty clear, right? I don't care what negative sine of x is. It's times 0, and that's 0, plus cosine of x times 1, and cosine of x times 1 is cosine x. There's my proof. What's my complaint? My complaints are many. Not the least of those complaints is that usually, as this is taught, professors forget to remind their students. I don't care if you're at Harvard. Sometimes we just need to be reminded that we have this sum and difference rule, and that's how he or she went from here to here. I mean, how the hell did they do that? Well, that's the explanation of that. And then also these special trig identities, like the fact that sine of x over x is equal to 1, like the fact that 1 minus cosine x over x is equal to 0. So that's how this works out. This, I think, is a better proof, and I hope that you agree. And if I made any mistakes or you have comments, please make them. And if you haven't already subscribed, please do. Thanks.